I am a data scientist at Skyscanner as of this week, but for the last 5 years I was working at the University of Cambridge on a research projects related to smartphones, so I'm going to be talking a little bit about that. So assumptions for this talk, that you've used Python before, that you've run into machine learning problems, and that you have a smartphone, which I'm guessing for this audience maybe a lot of you have more than one. So the cool thing obviously about smartphones is that they have sensors in them, and every time that another smartphone is released, they always advertise them with more sensors inside of them. And there's an interesting pattern in the research field, which is that every time a new device comes out with a new sensor in it, within a few months, researchers are publishing papers showing what sort of behaviors you can learn about the smartphone owner based on that. So just to give you some examples, obviously GPS is in all our phones now to support mapping, but it's also been used heavily to track people's mobility patterns, just like the orangutans in the previous talk. But also things that we wouldn't maybe consider as sensors, like the microphone and Bluetooth, have been used to study how we behave. So I think there's a famous project out of MIT that was looking at Bluetooth in the phone and detecting other Bluetooth sensors as a way of getting a signal of co-location, of two people hanging out with each other. So I'm going to be talking about the accelerometer. And when I first started with this research, I was told a story. And I'm going to tell you that story. I don't know if it's true, but let's pretend it's true. So the way it goes is that originally accelerometers were put into smartphones so that they could support landscape mode, and so that your phone would be able to detect when you move your phone from this position to that position, so that it could reset the interface. Of course, it didn't take very long to figure out that if you're carrying an accelerometer in your pocket all the time or in your bag, then you can use that same data to figure out a lot about how you're behaving in your everyday life. So in this talk, I'm just going to basically run you through maybe what was about 4 hours worth of work over the last couple of days. So collecting some data, taking a peek at the raw data, then putting it all together and building a classifier to figure out what I'm doing based on just raw accelerometer data. And everything is online here, including the talk, the Android app, and all the Python stuff. So let's dive in. The way I started was I built a very simple Android app. And from a user perspective, this is the way it looks. What I have to do is select an activity that I'm doing and click Start Sensing. And the app would begin collecting accelerometer data. And then when I'm done, I just click Stop. So that's the interaction behind creating my data set. Under the hood, Android, if you're writing in native Android, is in Java. And the paradigm is that the app is going to register a listener with the operating system. So it's going to say, I want to register with the sensor, which in this case is the accelerometer. So it's basically just saying to the device, give me some accelerometer data at this rate, sensor delay game. So the rate doesn't really matter for this talk, but game is quite a I guess, a fine-grained way of collecting accelerometer data. Maybe it's called game because you think of playing games on your phone. And when I click the Start button, so it registers, it says, start giving me data. When I click the Stop button, it says, OK, I'm done. Stop giving me data. And all my app was doing is it was writing that data into CSV files that I could just then pull straight off the device. So super hacky. Don't code review my app. But let's run right into the data. So an accelerometer is a very simple sensor that captures acceleration in 3 dimensions. So you can think of your phone as having maybe an x-axis, a y-axis, and a z-axis going this way. And so what the accelerometer is doing is feeling how much acceleration it's experiencing along these 3 dimensions. So you can look at the data as 3 time series. where you have the x, y, and z. And so what does that look like in practice? Well, the first activity I had was just standing, and these are the 3 axes. And pop quiz, why is this one hanging out around 9.6? Gravity. So the device isn't moving, but it's still feeling the acceleration of gravity, which is constant. In this case, it was on the z-axis. So let's go around to other activities. This is me walking, walking some laps in my back garden, running, and running actually, even though I have a twisted ankle right now, I was managing to max out the sensor in this particular device. Stairs, a little bit fake. I just had one stair, and I was going up and down it. Then this is me coming into London. So I was on the Metropolitan line, somewhere between, I think, Wembley Park and Finchley Road. And to be honest, it was in the morning, so I don't remember exactly what was happening. But this is the train. So one of the key things about this is that I've labeled this x, y, and z. But for all you know, there could be a bug in my code, and the axes could have been mislabeled. And that's a very important thing about this kind of data, is that if you were collecting it from some sort of app, it's kind of easy to get people to maybe label their activity sometimes. It's very difficult to get them to tell you precisely how their phone is oriented. So there have been some research studies where they are very prescriptive. They say, we're going to need you to collect data, but then put the phone in here or put the phone there. And it really takes things away from how they work in practice a little bit. So we need to start thinking about how can we work with this data and factor out the orientation aspect. So one of the ways that this is done is by taking all these 3 axes and combining them into one. And that's what's known as the magnitude vector. And so basically you're just taking the, let's see if I can get this right in one go, the square root of the sum of squares of each axis. So maybe I got that wrong, but let me show you what it looks like in practice. If I made the magnitude vector of each, it's clipped at the top. So this is standing, walking, running, stairs, and on that morning commute train. And now you can even start seeing visually that there is a difference in the different kinds of activities. And in particular, the one that stood out for me is that standing data looked quite noisy at first, but once we get the magnitude vector, we can see that it's quite flat. There's not that much going on. So what can we do with this data? Well, there are 3 things, and I'm going to focus on one, but I'll quickly mention the other 2. The first one is step counting. So I even have, I have it somewhere. It'll probably come ahead. So you can just count how many steps is a person taking. That's really an exercise in figuring out where steps happen in the data, and maybe even figuring out that the person is taking steps in the first place. And so there's a great paper that was published a few years ago about that. The second one is about profiling people, and I can tell you a little story about this, which is that a number of years ago we, in Cambridge, released an app that was collecting this accelerometer data. And it wasn't asking people what they're doing, but it was collecting that data. And instead, it was asking people how they feel. And so what we get, once we fold that data on top of each other, aggregate it, is a little signal like this. So one row of this is a person's typical day. And brighter colors means that they're being more active. Darker colors means they're being less active. And so you can imagine that as being your unique signature of how you live your daily life. And the reason why there are 3 groups is because we ran these profiles through a clustering algorithm to say what sort of different activities are in the data. And we had people who are really active all the way to people who don't seem to be moving at all. So the interesting thing here is that, like I said, the app was asking people how they feel. And what we found is there was a nice correlation between people who tend to feel more positive throughout their day and are happier were also up here. And the weird thing about that was obviously while I was doing all this analysis, I was very sedentary, so I was maybe a little bit down there. But like I said, the focus of this talk is looking more at activity classification. So a great example of that is the Google Fit app, which does do the step counting bit, which I was looking for earlier, but also is reporting 15 minutes of walking. It'll automatically detect cycling as well. And so what I want to give you in the next few slides is an intuition of how this works under the hood. So from a top level, we have these time series. And what we need to do is get these time series into some kind of manageable way that we can train a classifier. Then we can train a classifier, we can predict some activities, and we can put it into an app. We can use it for other quantified self experiments and these sort of things. So there's a very related problem to this, which is the problem of detecting entities in images. So I don't know if many of you have come across this before, but this was the very first Google image result for entity detection. And essentially, you can imagine an algorithm that, some kind of machine learning algorithm that will tell you, yes, there's an entity in this, or no, there's no entity in this. And so given a big picture, what you typically do is you take a square and you say, is there an entity in this square? And the algorithm says no. So then you just move the square over a little bit. And you say, is there an entity there? No. And this is called a sliding window problem, a sliding window approach. And so you take that square, you move it across your whole image, you move it maybe using whatever method you want. And at a certain point, it'll say, oh, yes, there's an entity here. And yes, there's an entity here. And basically, after querying your machine learning algorithm, hundreds of times, you will have found the 4 beetles. So we're doing a very similar thing, but with time series data. So we can define a window. And now we're going to walk across that window and say, what's going on here? What's going on here? What's going on here? And so in typical scenarios, that time window will be maybe 5 seconds or 10 seconds, but it depends on your application. But interestingly, we don't just use that as a way of testing the algorithm. We also use it as a way of extracting features to train the algorithm. So what do I mean by that? I mean that we take this data, the time series data, and for each window, we're going to extract a number of descriptive statistics or features. So again, there's a really good paper that explains this much better than I could in all this detail. But really what they do is they say that for each of these windows, there's a number of different characteristics that we can extract from. And they talk about a whole family, maybe 5 different categories of these characteristics. But you can take these sort of 3. So in this window, what are some statistical characteristics like the average, the minimum, the maximum, the standard deviation? What are some characteristics of the time series, like the jitter, which I'll get to, or you can go on and dream up as many features as you want. So I'll look at 2 that I implemented. The first one is measuring, like I said, jitter in the signal, and really all that's doing is it's looking at the difference between the previous measurement and the current measurement. So if we go back to our example, you can say, oh, look, if there's, this reading was down here, the next reading is up here, and the next reading is down here, the next reading is up there, that's high jitter. Otherwise, if you have a reading here, and then up there, and then down here, and then up there, that's very low jitter. So that's one thing that we could look at. The second thing is maybe more, is somewhat similar. You could look at what's called a mean crossing rate. And I'll give you 2 examples that highlight this. So imagine a signal that is very high and stable, and then it drops, and then it's very low and stable. So your mean is somewhere in the middle of that. And by being very high and then dropping and then being very low, it's crossed the mean once. So this type of time series has a very low mean crossing rate. On the other hand, imagine a signal that goes like this, right? And it's doing that very fast. So it's got maybe even some high jitter characteristics. So again, the mean of that signal is somewhere in the middle. But since it's been going up and down and up and down and up and down, it's got a very high mean crossing rate. So these are two features that I implemented myself. But the nice thing, obviously, about Python is that there's loads of features and loads of libraries that implement things that are maybe even a bit more complex to implement. So the two that I was looking at were stats models and SciPy stats has skew and kurtosis. Again, I wouldn't even be able to write the math for that just off the top of my head. And stats models has cool things like the autocorrelation and the autocovariance. So really all I was doing is taking all these features and producing a list. And what that means is that for every single window in my data, I'm looking at what are the features of the x-axis, y-axis, and the magnitude vector. Then I'm moving the window over. What are the features there? Then I'm moving my window over. And to make a long story short, I'm just creating a nice data frame where I say, I know what's going on here because I've labeled it. I've said I'm walking here. And here's a list of representing all the features of the x-axis first, then the y-axis, then the z-axis, then the magnitude vector. So once we're there, now things, thankfully for Python and scikit-learn, get pretty easy, right? So we have the data in a nice format, and all we have to do is just load it into scikit-learn. And in this case, what I wanted to do was actually see whether I can predict what activity I'm doing and whether I can predict what activity I'm doing better than some kind of dumb baseline. So the dumb baseline is what in scikit-learn is called the dummy classifier. And I'm sure some of you have run into it before. And all that is doing by default is it's, as it says in the documentation, generating predictions by respecting the training set's class distribution. So what that means, if I have 5 classes, they're uniformly distributed, there's the same amount of data for each class, then I'd expect, by picking a class at random, I'd expect to be about 20% accurate overall. And what I'd hope is for the random forest to be, which uses the data, to do a little bit better than that. So all I do is I repeat this experiment 10 times, and I split the data set into 60% that is going to be used to train the algorithm, 40% that is going to be used to test it, and then I run it through both of these classifiers, so the random forest and the baseline. And I score them. The default scoring, I think, is accuracy. So the gist behind that is if we predict walking and it is walking, then it's +1. If we predict running and it's walking, then that's a 0. So run through the 10 experiments and average them, and we do find that the baseline is about 20%. It's a little bit higher, but the random forest goes all the way up to 98%, which is a very impressive number to report, but of course there's a number of limitations here. So that was basically Thursday night I hacked together the app, and at about 1 a.m. I started running around. And last night after work I did the feature stuff and the experiments. So really what you've seen today is a very simple explanation of this problem. And especially it's a very simplified version of this problem because it's not super realistic. So there are a number of other things that can make this problem a lot more complicated. But the main thing that I wanted to highlight was the method that I use to train these algorithms. So what things can make this more complicated? This is along the entire pipeline, starting from collecting the data. So if you are going to build an app that is collecting accelerometer data, the app that I made, as soon as you press the home button, it stops collecting data. So if you don't have this app active on the front. It just doesn't collect any data. So there's ways of, on Android, on iOS, it's a whole different story, on Android of collecting this data in the background, but then you need to start considering about how frequently you're collecting the data, what sampling rate you're using, should you stop sensing when you're not detecting any activity, because ultimately, if you are just collecting data all the time, you can write an app that does this, and it'll burn through the battery within a few hours, and people will uninstall your app and write you angry emails. The real data is certainly messier. This example, just me, just one phone, just one sensor, and there are differences across devices. And in particular, with the data from the public apps that we were using, we had to denoise it a lot. There were even some instances of things that we saw that were impossibly high amounts of acceleration, as if they were, shooting up to the moon or something. And I'm assuming that no one in the space station right now had my app installed. So when it came to features, what you saw today was me just throwing everything at the problem, which is sometimes nice, but there are many other different kinds of features that you could use. And finally, probably the most important thing is that the machine learning problem that I showed you is really about detecting one of 5 activities. But there are many more different things that you can do. So for example, you could turn it into a binary classification problem and say, is the person walking right now? And that's actually probably more realistic because you can't train for all of the activities that are possible. So it's more likely that you will train a model on one activity that you want to identify and train it against data where you just know that it's not that activity. And finally, again, as a consequence of being just one person, the data I showed you was trained on me and then tested on me. And in practice, you're going to be there are some images online of famous tech companies that strap phones to their employees and ask them to perform activities like cycle and walk. And they use that as their training data, but then they're going to be trying to predict other people. So that makes things much more complicated. And one way that you can get around that is by, as you're collecting data from those other people, you use that to tailor your model and make personalized predictions. So can I identify that I am walking versus other people? So just to wrap up, quick hack over the last 2 nights, all the way from collecting accelerometer data to classifying it. And what I hope to have shown you is that this is actually easier to hack at than what I originally thought when I was approaching this problem. And really what this does is it's starting to open up a lot of research going towards a lot of new mobile applications that are going to be using these kind of techniques on different kinds of sensor data in order to make the user experience better. So just as an example, one of the last projects that I was working on in Cambridge was related to smoking cessation. And what we wanted to do was detect when people are most likely to smoke. So we had them telling us when they were smoking, and then we used similar techniques. In this case, it wasn't with accelerometer data, but it was with location data to make inferences about the risk that they are for smoking at particular times and places and so forth. And when the algorithm detected that risk, they were fired off some nice cognitive behavioral therapy that would help to keep them motivated to keep up with their quit attempts. So, like I said, everything is online. Happy for you to report in any bugs to me or take this code and do whatever you want with it. And with that, thank you very much. Happy to take any questions.
Thank you. Any questions?
How do you decide the size of the window?
Sorry?
How do you decide the size of the window?
The size of the window is, in my experience, it's a heuristic that you have to play with. So the way that I decided when I was doing the research was I asked other researchers what windows they use, and the answers came back usually like on the 5 to 20 second side. But in practice, I think it relates to whatever high-level goal you have in your app.
I wonder if you're familiar with any techniques you might use in this context for class discovery. So say you've never seen somebody, I don't know, riding a bike, or all these different things you know are in your data set, but you don't know what classes are there. How would you discover what's there? I was starting to have a stab at this, and it's, the approach that I was using was trying to throw different clustering algorithms at it. The problem is that when you're dealing with a data set from the public, you can't validate it. You can just say, this is something that I've never seen before, and I'm not sure where it is. And when you're dealing with a data set that you made, it's too simplistic, right? So what we found in the data from the public was that even certain activities that we had people reporting, there was a huge variability in those activities. So the way that I walk versus maybe the way my grandmother walks or something. Not that any grandmothers were probably using my app. But so very challenging problem. And the main challenge behind it is that so many activities, from a feature perspective, it's very difficult to say that this is a completely new activity versus this is a variant of an activity that I've seen before. Final comment on that, one of the ways that we were also looking at this was by watches and collecting data from two devices from the same person at the same time and looking at variability there. And that, again, highlighted that the same activity can produce very different data. So, just another challenge.
So going to accelerometer, somebody standing or somebody skydiving.
Yeah.
Without a parachute.
Yeah.
Same thing.
Yeah, I guess so. I guess just. Oh yes, that's true. There you go. You'd have canceled that one out. I never really thought too much about the skydiving scenario, to be honest. Yeah. Yep. Binary feature. Very unlikely prior, probably. Yes? Yeah.
Are there any gotchas as far as like metrics that might seem intuitively useful that you found will lead down the wrong path?
Sorry, can you say that again?
Any way of characterizing the data that might feel intuitive but is actually totally wrong?
Yeah. The initial, I probably should have mentioned this. Like my first line of exploration was into time series modeling, and this is me having never done any smartphone machine learning stuff and thinking, oh, accelerometers produce time series data, so let me look at time series modeling. And a lot of time series forecasting is about forecasting maybe even the shape of the time series, and that's not so relevant to doing solving these kind of problems where the actual shape of the accelerometer time series is not as important as the features of that shape, right? Hope that that's one thing that I messed up on, but I could probably think of a lot more.
I think that's quite an interesting point. That's interesting because coming from time series forecasting background, I consider all time series things forecasting problems.
Yep.
Yeah. The whole feature extraction is quite interesting.
Actually, I have two questions. The first question is, when you train the model in random forest, how was actually the class balances? Because I usually would assume that people stand more than working, right? Or
Yeah. So yeah, that's a very good point. This is a toy example where I manually balanced all the data, and my original data set, maybe it's the one that's on GitHub, does have more standing than walking, and certainly I think in the end I had to prune it because I ran the least.
So I pruned all the other data down to as much running as I had. Yeah, in practice, I think you would probably be looking at a one versus all type of problem. So even in those problems, you have very unbalanced data. What was your second question?
The second question is, have you actually looked at LSTM models? Because actually the way how you do it is perfectly with this kind of model, because then you don't need the feature.
Yeah, that's true. I haven't. I'm completely new to that. I'm just starting to hack with it. And I know there are some researchers who are looking at it, and they're even looking at it from the point of view of running the LSTM on the device itself, which has some cool like privacy preserving aspects, because then you're just maybe transmitting the output of that. But short answer, no, I haven't. Yep.
Have you looked into how someone walks and runs as that individual characteristic? Like running is different from walking for that person, and the difference is the same for all person, but the threshold level is not the same for every person. Like running is courtesy is plus 20% than walking, so if you don't know how that person walks, you can't tell if that is running or walking.
Yeah.
If you are very dynamic, so you're always high energy, and your grandmother is never that dynamic. So when she runs, she deploys as much courtesy as you do when you walk. That kind of individual level model.
That's a good point. I haven't looked at that. No. Maybe I'll try it one of these evenings. Yes.
Is there any reason why at this stage you didn't use the gyro data as well? Because the gyro plus accelerometer, in principle, you should be able to reconstruct sort of the three-dimensional position.
That's a very good point, and I probably should have mentioned it in my final thoughts. Layering in other sensors is, as far as I've been able to see, one of the most widely practiced ways of sensing with more energy efficiency, and then also squeezing a bit more out of your data. I left the gyro out just to keep this simple, but a very neat example of this in practice is treating your sensor sampling kind of like TCP on the web, where you sample from the sensor, and if you don't really, or you sample from a family of sensors like location and accelerometer, and then if you don't detect a change in one sensor, you turn off the other ones, right? So, oh, we're still in the same place. Oh, we're still in the same place. So, or, oh, we're in a very different place. Let's ramp up how much activity we're sensing. Maybe Neal has left his house and has started walking. So those, a lot of those systems are still very heuristic-based, like the example I just gave. But yeah, I haven't really seen in those kind of models in practice. But I have a feeling probably the Google Fit app does some of that cool stuff. Yeah.
Have you compared your model without combining the three axes in the same time series?
No, I haven't. And I think by having the three axes, it made my results more impressive. But because in practice, maybe what was happening in my data mostly on the x-axis would be distributed across the three axes in a larger, more realistic data set. But I would class that under a sort of broader exercise in feature engineering. And some of the features that I described today, you could probably junk because they're probably highly correlated with each other. So that's the cool thing about random forest, is that you can inspect that and then throw some away or think about adding in some more. Well done. Thank you very much.